great having you here for the second talk in 1 week. But they're both excellent talks, and today we have the honor of having Ivan and Laptev present to us. Well, probably you already know that, but Ivan is one of the biggest names in computer vision and video understanding. But in more detail about him, he's a senior researcher at INVIA Paris and the head of the scientific board at Vision Labs. He received a PhD degree in computer science from the Royal Institute of Technology in 2004 and a habilitation degree from the Qualcomm-UvA in 2013. Ivan's main research interests in visual recognition of human actions, objects, and interactions, and more recently robotics. He has published over 7 papers at international conferences and journals in computer vision and machine learning. He serves as an associate editor of IJCV and TPAMI, and he has served as a program chair for CVPR 18 and the regular area chair for CVPR ICV and ECV. He has organized several tutorials, workshops, and challenges at major computer vision conferences. He has also co-organized a series of media summer schools of computer vision and machine learning and Machines Can See summits. He received the New Year's Starting Award in 2012 and was awarded a Helmut's Prize in 2017. So let's thank you.
Yeah.
Big bio for big name.
Thanks, Stratis, for the impressive introduction. And thanks a lot for inviting me here. I'm really glad to be. I think it's the first time really I'm here, so the place looks impressive. So let me talk about what I'm doing mostly in research, and then at the very end also I'll show a few slides of my other life, which is a company. So the introduction. So the introduction is that we now have great machines which can do lots of things for us. So as you know, the convolutional nets, so they can do pose estimation, they can do object recognition, they can do segmentation. So this is all what came in the last few years. So this is really impressive. So people who've been, like me, been in computer vision for 15, 20 years, this looks really impressive. Like my blood still pumps when I see these results. And but for example, when I show it to my 15-year-old daughter, so she says, "Okay, this just works." Okay, that's fine too. So okay, that means that we have something else to do. Well, or the new generation, they will just have it for granted and go forward. So that's good. But still, so it seems that we have these machines which suddenly can do so much great things for us. It seems that CNNs can learn almost anything. And actually they can learn almost anything. So this is an example of work where it's done by our previous students. So they just take the random labels, they take ImageNet. There is some matrix in between which is basically says one image, one label, not one image, multi-label not, but basically it's a random labeling with a constraint that one image is one label. Okay, and then and this matrix is learned during optimization. So but basically this is producing already very good features. So CNN can learn just random labels, and already if you use this pre-trained representation of something else, this gives great results. So why I'm talking about this? Because so assuming CNNs, of course, there's lots of interesting research going on how to make CNNs better, faster, how to address new tasks. Of course, that's very interesting. And we have not solved this. Probably the curve's saturating now, but still we believe there is still lots of interesting things to do. But another interesting question in this regard, so if we have these great machines which can do so much for us already, so what are the tasks which we are giving to these machines? And like how to solve the task, it seems, well, at least to me, it's interesting also to look at the question, what are the proxy tasks are we giving to machines? And so one proxy task, as we all know, is a classification. So for actions specifically, this gets a bit ambiguous, or the granularity is a problem. So if you open a dictionary and try to, or ask people on Mechanical Turk to label images by actions, this can be, some people will say it's open, some people will say it's like open umbrella, open door. So where do you pick the right level of granularity? Unclear. So now the example, so here, apparently all people are running, and so if you give people more context, so probably people will label it differently. So now the example is, okay, so even if we somehow handle these problems of ambiguity and granularity, there is still a question. So if we are interested in just in the proxy tasks of labeling things, how far does it bring us? So can we, for example, solve this type of predictions, or can we reason really that if you pull table close, what will happen next? Maybe if you have collected 10,000 examples of people pulling the table close, yes, probably you will. But this is not scalable approach, so you need something which is compositional, which can reason on the high level, and high level basically means that something which we cannot do now, I think. So if you would solve it, probably we would not talk about it as very high level. But I think like these examples we cannot do now, and it would be great to do in the future. So what are the more practical applications for vision, for actions? So these are two types of scenarios which we are interested long term. So one is like robotics. Obviously, this is where the robots need to perform actions. They probably sometimes they have to do it in a collaboration with people. So a kitchen robot, maybe you come and you do something, and then the kitchen robot will do something else. So the robots eventually will collaborate with each other also. But even before that, so the probably simpler task is to give instructions to people, use people as a kind of a perfect, not perfect, but advanced machine, which is already mechanically very good, but just not always knowing how to do things. And so giving instructions to people how to do things would be great. I think the Microsoft HoloLens is trying to do it now, and I imagine some other companies as well. Okay, so this is a set of applications which are interesting, and now the question is so if we want to solve these tasks, so it would be great if we could, for example, learn from people. Okay, so to perform, like, give instructions or how to prepare the meals. The question is how should we interpret human actions or videos of people? So what are the primitives? What are the good proxy tasks to solve? What are the primitives? What are action classes or something else which we should consider? Given the problems which I just mentioned in the beginning, we believe it might be more useful to look maybe at a more constrained problem, but which is defined by the goal. So here are instructional videos, and instructional videos, they are well, they have a clear goal. Or so here there is a task of assembling IKEA furniture. It's a clear task. Well, it's a task with a clear outcome. So, and then to achieve this outcome, there should be some actions performed, obviously. So now, what actions? It's they could be different set of actions, and actually, doesn't matter how we call them or which are included in the set or not. So the important thing is that it should bring us from state 1 to state 2. Okay, and that's maybe the best way to define the action. So we don't need to do Mechanical Turk or come up what is the good granularity of the labels, or what is, like, deal with ambiguity. So just make the computer itself come up with the primitives. So having action primitives, some latent variable, which would be sufficient to get this state to this state. Okay. By the way, so if you have any questions, so please ask. So this is was motivating part. So now for the actual work we've been doing in this direction. So we are, as I said, so we worked with movies before. So movies are a great source of data that you have a video, it's fun. So you have scripts, so you can align video track to the text track. This gives you some supervision. We can learn many things, but this is very generic. So this is a more narrow domain, instructional videos. But we think it's still very interesting for many reasons. So one is, as I said before, it's goal-driven. So it's you don't just have the random, or not random, but like in the movie, very diverse set of things. So you have a goal, and the actions which are performed, they are there to achieve the goal. And for the same task, you can get from internet lots of different videos. With lots of variability of people, objects, and so on. Okay, so also these are videos which are done by people to teach other people, and they talk, they narrate. Okay, so here is a narration which you see, and YouTube is getting, so we've been looking at these videos for 3-4 years, and over these years YouTube got much better in transcription. So it's now, in the beginning it was quite crappy, now it's maybe 80-90% is pretty good. And so if you're interested in this, one practical tip is that you can download these narrations, transcribed narrations, even without downloading the videos. So you can, that's generally for YouTube. So if you want to do fast filtering of what videos you are interested in, so you just download narrations, and then you do some filtering on them, and then you download the videos. So that helps if you want to do large scale. So what do we do with these videos? So here are 3 papers we've done. It's not solving the big problem which I eventually would like to solve, but it's solving some sub-problems under assumptions. And so these 3 papers, basically they have different assumptions. So the first one, what is the task? You want to discover, in the first paper, want to discover what are the actions which will lead from state 0 to the target state. Okay, and this done under assumptions that critical actions, they should repeat. So if you have several videos of the same task, all of them should appear in all the videos, and they should appear in the same order. It's a bit of restricting assumptions, but it's not always true, but it's often true, and it helps. So another assumption was look at the states of the object states and connecting them to actions. And the last paper is about going larger scale. If you go larger scale, then we can start sharing actions between tasks. So okay, I'll talk about this. And so this is going to be the first part. So I hope to, so I'm going quite briefly over this. So the first paper is already a few years back. Maybe you've seen this. So if you have not seen instructional videos, so here's example. All right. So how many of them? Okay, I'm not going to play it. And so what are the problems? So what is the data? Data is, so we have video tracks and text for many different videos of the same tasks. So you just change the car tire in a search, you get many videos. Some of them will be not relevant. Okay, you can filter it or not filter, but say if you now have a relevant video, so you can, these are, say, the 3 steps you want to discover. So there are more, but just as an example. And then, so you assume that these steps, they will appear both in the text and in the video. So it becomes a clustering problem. So you want find clusters for one step. You want to find a cluster of appearance. So you assume that, say, loosened nuts or jack car would look somewhat similar in different videos. You also assume that they will, in the text, they will be expressed in a similar way. And also you assume that the video and the corresponding description in time, they will be roughly aligned. So all of this is noisy, of course, so that's what makes the problem harder. So because there is a variability in the text, so the same action can be expressed in different ways. There's a variability in the action, same action can be done in different ways, and also there is ambiguity in the alignment, because people sometimes they talk and then they do, sometimes they talk and do it at the same time, sometimes they, well, all kinds of variations. So if very briefly about the method, it's a simple, here it's a simple linear model. Of course, you can use whatever features, you can fine tune them. But say if you have features X and the linear classifier, and these are your labels, then this is a cost function standard. What is less standard, that these labels, they are not given. So this is the discovery part. Okay, so what is the X? We are in this work, so we are on the clip level. So we have a long video, we subdivide it into short clips. This is X, okay? And then each X should be classified. This is the classifier, so we want to learn a classifier. Classified to what? To a set of actions. And what are the actions? We don't know. So you want to discover the actions. That's why Z is not given. So Z is a label matrix, okay? Like Z is dimensions of number of classes and the number of clips which you consider. And so you want to assign this matrix during training. Okay, so like if this would be given, this would be standard like supervised classification. This is not given, it's unsupervised, but it's not completely unsupervised because we want to use constraints which we have from text. Right, so we assume text is aligned with the video, and so here are the constraints. So it constrains the order of steps. So we have to give the number. So say we want to discover 5 actions or 10 actions in a task, and then there is an ordering constraint which cannot be written explicitly, but it can be easily enforced by dynamic programming at the optimization that you want the actions to be in the same order. So okay, and that helps. Like without this constraint, it will not work. But with these and a few other constraints, it works. So it does find something like this. So so here are examples of actions which are discovered automatically. And then the so videos where the steps where the actions are discovered. Okay, so yeah, I will go briefly about all this. But if you have any questions, please interrupt. So here's another work we've done, which is looking at actions and states. So trying to the idea of connecting the action and state. So assumption is that actions are often there to modify the world from some state to another state. So here we assume that actions are modifying the objects. And many examples. So this is what the method does for. Okay, maybe I'll show later examples. But so there are. Well, you can have opening doors. So the door is first closed and open. You can. In many situations, the actions modify the objects. So and here, so we try to connect both. So we try to discover the action and to find out the. What are the states of the objects? And in this case, so here the algorithm finds that the state 1 is the cup is empty, there is action, and in state 2 it's full. Okay, so we don't actually know that what is the name of the step. This is done just manually because in instructional videos people don't say now cup is empty, now I'm filling it up, now the cup is full. That's too much to expect from this data. But if you assume that for action this is true, then okay. There are a few assumptions here, so it's so we assume that we know that pouring into a cup involves a cup, so we grab just a cup detector from somewhere and run it, and then but the goal is to cluster the states of the cup, so then the algorithm automatically finds out that the cups before the action they are empty, and what does it mean? So these are representations, well, the examples of empty cups, and after the action they're full. Okay, so same for changing car tire. So it's before putting the wheel and after putting the wheel. The appearance is different, so it can cluster it. Opening the fridge. Yeah, so okay, we believe we just scratched the surface, so there is more things to do, for example, for opening a fridge or opening a door. So there is also, so if you would consider closing a door, then you could either discover or maybe put the knowledge that there are opposite actions than the state of objects. Like in opening, it would be first closed, then opened, and in closing, it would be the opposite. Maybe you could exploit this constraint as well. Yeah.
In this action, opening the fridge, right? This implies that he's moving the hand. So why do you go for open the fridge instead of moving your hand? I mean, how do you this granularity? How do you stop? Where do you stop?
Well, we are not looking at the hand explicitly here, so it's on a level of the whole video.
So the actions are predefined for
Um,
the list of actions.
Yeah, in this case, so as we assume that we have discovered some key actions, and one of them is open, so we just get the clip where we know open happens from the text. It mentions open, so we just take the clips where open happens, but we don't know where in time, and we know that there is a fridge involved, and we want to discover when the action happens and what is the state 1, state 2 before and after the action. What's the appearance of the fridge? So that's the setup. So your question, why don't we look at the hand, for example, that it's
let's leave the questions for later, otherwise we don't want to.
Sorry, yeah. he has the power. Okay, so this table just shows that if you solve, so there are two sub-problems here: finding when the action happens and clustering the objects into state 1, state 2. So you can attempt solving this problem separately or together, and then well, basically this table says that solving them jointly is better. Okay, so the performance, if you see, numbers are still pretty low. So if you want to make a startup on this direction, that you will need to work still quite hard. But this is work in progress, and so the main result is that yes, it's joint. Like first, it makes sense to do this assumption of that the action changes state of objects is true often, and then it also helps to solve it together. Okay, so that was first type of work. So it got us interested in instructional videos. So we realized that there are really a lot of them. So there is sites like WikiHow, and they have tens of thousands of tasks in a sense that they describe how things work or how you meet your wife or husband. And this is not what we are currently interested in, but so we filter manually them into what is visually related, what is visually. So tasks which are visually grounded and which are not visually grounded. So we look at. So this work was CPR19. So it's going to more tasks. I think the order is about 100, maybe a bit less. So interesting thing when you go to more tasks is that you can start sharing. You can assume that you can share the actions between tasks. So say pouring will happen in making pancakes or making lemonade, and so on. Right, so that seems to be a good thing. So here's the model, which is now which we call component models. It's a quite simple additive model which allows us to share actions between tasks, but also compose each action composed of multiple components. And the component would be like pour or milk or whisk or mixture, and they are trained, all of this is trained together, of course, but okay, it's an additive model, and in terms of formula, so it's here. So each G, it's a classifier for each of these components, and they are mixed into action. So A is a mixture matrix. Each row would be ones for the component. So each row would be an action, and it will be 0 ones. So 1 is the component is included into actions, and 0 otherwise. I think we're actually giving this by hand. So this is a per task matrix. So it's so you only do it once per task, so it's not much manual work. Of course, ideally would discover it automatically, but it's already all the process is quite noisy. So starting with a noisy transcription, so we thought that we limit it a bit and give it by hand. Nothing special. So then it's trained with the standard losses. You can fine-tune or you don't fine-tune, depends how much resources you have. I think here we didn't have much resources, so we didn't. The data set, as I said, so it's 83 different tasks, so it's comparable to the largest other data sets like you cook, but it's not just about cooking, it's about more tasks, and it has temporal annotation, so we can actually do action detection. So here, few numbers. So what happens if you so the initial goal was to try to see if we can benefit from a data by sharing the actions, by learning actions shared between tasks, and that's what you gain here, guys. If you not do sharing, and this is what you do if you do sharing, so then you can also get more gains very easily by just looking into what we call related tasks. So we have 18 tasks which are where we have full annotation for testing, so we can observe everything what happens, analyze, but then so we have them for training and testing. But then we can have, because everything is unsupervised, so we can just get from internet other examples for other tasks and assume that the actions will be shared. Of course, if you take just random tasks, the chance that the actions will be shared with our 18 target tasks is maybe small, so therefore we take some tasks which are similar to the ones we have, similar to the 18 tasks, and then we just include it into training, and it does bring improvements. And one more thing one can do with this component model is to look at tasks and actions which have never seen before in a training. So here's add strawberry in a making cake scenario. So this has not been in the training, but because we have seen already add and we've seen strawberry in some other tasks, so it helps. And this is the curve where, so if we increase the number of training tasks and measure what is the performance on unseen tasks, so it keeps increasing, which is good. Yeah. This one? Yeah. That's the random, that's the chance. Yeah. Yeah. Okay, and now, so, 80 tasks. So given that there are lots of tasks, so 80 tasks still seems not very much. And on internet, there are really lots of these videos. Seems maybe this domain just becomes popular. People are uploading lots of these videos. So, so now we just try to exploit all the WikiHow and as I said before, so we had some manual filtering on the level of tasks, so just saying that this task is more relevant for us, this is not. And so I ended up with 23,000 tasks. So downloaded videos for about 100, 200 videos for all of them. After this manual, automatic, of course, the pre-filtering of text, maybe some other filters, like there are slideshows, there are some uninteresting things. So I ended up with this number of videos. And now if you look at so what transcriptions, they are separated by some time when people don't talk. So we just take small pieces of text and corresponding videos as clips, and then you end up with 100 million clips. This was 1.5 student project in a lab, so it's you don't need to be at the Google scale or so to do this. So it's all quite possible. And so what are the problems actually associated? What can we do with it? So one, especially at this scale, because at this scale, it's like having more precise modeling of ordering and other things is becoming a bit complicated because we have used some, well, it just becomes too complicated. So we thought, okay, let's just try to do something simple, and something simple would be to, say, address the task of video retrieval by text, video retrieval by text. Standard task, we did not really contribute anything to the method, so just, again, so you can fine-tune or not the features, so you have some initial embedding for video, initial embedding for text. Again, so we are looking at the level of clips, right? Each sample is a clip and adjusted text. Okay, and then we just want to learn something here or altogether that the corresponding text and the video, they are close in the feature space, and if they are not corresponding, probably they should be far apart. Okay, and then if you have this joint embedding, then it's trivial to do retrieval. You just have either by text or by image. So you have you encode text, you have nearest neighbor, the video. Okay, so and this task is not new. So there have been a few data sets and challenges on this. The largest one, well, it's something around maybe 1,000, and okay, or about, okay, most of them they're 100 hours, and we are 1,000 times more. And but of course, difference that this is all manually curated, and that's probably the amount where you can go with manual annotations. So if you want to manually annotate this, I don't know, maybe Google can do it. I don't know. Probably, I think it will be still very hard. I mean, we know kinetics, they are getting to progressing slowly to now 600 classes or 800 classes. So it's quite slow process. So because this is automatic, of course, it has noise. So the noise level, according to our estimate, is about 50%, which is quite high. And we try to, that's where I said that we don't have something new to the method. Actually, we did try to be a bit clever and to try to automatically filter the noise out by doing some multiple instance learning during training, trying to figure out which videos actually do correspond with the text, which not, to remove it during training. So far, didn't help. We don't know why. Either the method is not very good, or maybe for some reason this noise level is not so important. So far, hard to say. So these are some results, and so I'll show. So by the way, the demo is online, so you can go to this link and acquire many things in this 100 million clip data set. So what I'm showing here is some queries, like they're becoming increasingly complicated. So like cut was cut, so cut wood, cut paper, so see, and then so it can go more fine grain, like cut paper in circle. Of course, it doesn't always work, so you'll see if you try it out yourself, but still it's interesting that it does work for some complicated examples like cut paper and circle. Then we can have hold wine glass, fill wine glass. So it seems that this effect is, well, that's our explanation, so it seems that it's purely by the data, so actually, yes, so that's some results. So does data help? Yes. So if you, this is a performance on the task of the previous paper, CPR 19 paper, which I've shown before, where we try to discover the actions with these ordering constraints. He actually doesn't use any ordering constraints, just learns the text to video embedding, and then we try to retrieve the actions from the CPR 19 setup. And the more data put into training embedding, so the better it helps, the better it goes. And this is also true for other retrieval tasks. So this is more standard. I think this is a standard video retrieval task. On UCook, I don't know if people done retrieval before. This is also a standard retrieval task. So we see that it all goes up. It's a logarithmic scale, but okay, it's not saturating. So more data helps. Well, these are obvious. These are frequent conclusions. Maybe it's still interesting that on the scale of 100 million for video retrieval, it has not been. We have not seen this yet. So just a confirmation. You can see this paper, just a confirmation. Yes, you get the data helps, but also there is a instructional video is a good way maybe to get the data for text video retrieval. So in terms of more numbers, confirming that it is good data. So there are two data sets. UCook is instructional videos. For cooking, this is more generic data set from YouTube. And okay, what we look at, so if we just train our embedding only on UCook data, so we get a comparable performance. This line is just showing that our sort of method is fine. Is not like much better or worse than the standard baselines. And then if we train it on just on our data, not UCook. So UCook was collected and manually, I think, labeled. And so if we just do it with our data without any manual annotation, so we get better results, and then even better results if we combine. Now what happens on this data set, which is not instructional, this is more generic data set. Here, if we train only on our data set, results are somewhat worse than if you train it on the target data set, right? And this is kind of expected because domains are different. Still, it gets quite reasonable performance, and then if you combine, then you win. Okay, so any short questions to this part? Or we can take it later. So now back to some motivating examples of what I've shown so far. It's very coarse level, so it's maybe just finding a piece of video corresponding to text, or maybe finding an action which is important for a task on a video level. So if you want to give instructions here to the person that maybe she's holding it like 10 degrees wrong, so the video level classification, or so may not be enough. So that's why we are also looking at this type of problems of precise modeling of 3D geometry for just images like this. So there is quite some work on estimating pose for hands and pose for objects from 3D data, Kinect. This is, of course, interesting. We are more looking into RGB images. because we want to, for the training at least, we want to gather, eventually want to profit from all the data which is already on internet, and this data is not 3D, so it's so you want to be able to analyze RGB images. Okay, so the challenge here is also the data and evaluation, but even the training data is very hard because annotating hands, 3D hands, it's kind of possible. Okay, CMU shown this. So I think the Michael Black's lab, they also are doing this because hands are varied, but not so much between people, so you can model it quite well. Objects, if you want to do thousands of different objects, that's very hard. So even if you have Kinect 3D data, so it will still be a and if you maybe can fit the model to the 3D data, it works, but then you have to have models for the types of objects, so very, very complicated. So there is I think only one data set where they have hands and objects 3D annotated. Been quite some, so it's called first person hand benchmark. So it has, I imagine, has been quite some work to do it. Still, well, we see artifacts for the hands because they have to measure the position. And object annotation, what we found, I think it's not very precise. If you really want to measure the precise localization of objects, 5 minutes?
Yeah.
Wow. Okay. Okay, so in terms of data, so that's the trick we are currently using. So we found software from actually quite old robotic software called Graspit. So they given an object in the hand, so they try to close the hand such that the object is stable in the hand, and we can automatically generate millions of grasps, render it. So these grasps are not, they are physically stable, but they are not maybe supernatural. So it just, so like because there is much of how you hold the phone. It's well, it depends not only that it should be stable, but it also how you use it. So still, so this is a data set, and this is the model where we sort of combine two networks which people have looked at before for hand reconstruction and for object reconstruction. Object reconstruction is AtlasNet. And the novelty is that there is a contact loss where we impose some physical constraints. So the idea here is try to not just do objects and hands separately, but do it jointly, and not just jointly, but also exploit some more knowledge which we know. Constraints constraints are that if the object is held in a hand, it should not be dropping out of the hand, so it should have contact, and then the hand should not penetrate the object, and vice versa. So these are basically the two constraints in the loss, and as far as we can measure, it does help, but measurements in this domain are still complex because of the noise and scarce of the annotation, even for the test set. Anyway, so here are some results. Does reconstruct, okay, it's not trivial reconstruct, so it should be able to reconstruct any objects. Of course, there are some limitations, but okay, it does get, it's not just blobs, so it does find quite different shapes. Sometimes fails, probably here, didn't know. Okay, I'd assume that this thing is, okay, that's all in speculation, but it's understandable why it makes these mistakes. Okay, so to end up, so one more, okay, sort of closing the story. So we looked at instructional videos. We are looking at more precise measurements. Also, eventually to reconstruct instructional videos and to get more fine-grained knowledge, in order to provide instructions, to automatic instructions to people, or to learn robots how to do things. But one big drawback with instructional videos is that they never show failure, so very rarely. And we know that if you want to train something, we need negative examples. Okay, so this data, it's very good data, but it's probably not sufficient. On the other hand, robots, it's the opposite. They always fail. So that's why we also start looking at robots. We want to combine this. We had some attempts on the level of few master students trying to learn robots, or at least simulators from instructional videos. Okay, still very hard. So we're just starting looking at robots, and so one work which is still ongoing, not published yet, but so we are, I guess this is our first robotics work, so we are excited. So what, if now switching the gears, so in robotics, well, the robotics very long, has a long history, and so recently there is a more learning for robotics. It seems to make sense to learn visual representations for robotics, so we can go directly from pixels to actions. There are drawbacks of this, but there are also obvious benefits, because if you make interface that I'm first detecting an object and then doing something with these 3D models, so there is this, at this interface there is an error which will accumulate, and so if you can do end-to-end, hopefully it should be better. So that's the overall motivation for us. So, but then the people who do learning in robotics, they usually do something simple, grasping. We've seen great papers from Berkeley, from CMU. They maybe push, grasp, simple things. So we want to go further. We want to learn long tasks. And here our longest task for now is to what we call breakfast. So there are, this is depth data, so there is a bottle and object, and bottle and a cup and the bowl, and the robot has to pick each of them, pour into the bowl, and put them in the right place. So, and the model is, so we have two levels. So one is more supervised, which is pre-trained actions. So simple actions like grasp, pour, put object into free space. So these are primitive actions, and they are learned more supervisedly. So it's all learned, by the way, in simulator and then applied to real. We have sim to real transfer, which is kind of working well. So we don't care about real for now. So we can afford to train on many samples. So we do take maybe like hundreds, thousands of examples to train primitive actions like grasping. Okay. And then once this is done, so there is a second level which is implemented as a reinforcement learning, where we try to combine the primitive actions into longer tasks. Okay? And this is done without what is called with a sparse reward. So problem in robotics and in general with reinforcement learning, that like when you train Atari games or so often, so the intermediate rewards are very important. So like the score which you see on the screen, this is like a very strong signal, supervisory signal for reinforcement learning. You see, if you don't have this is people know it's a big problem. So here we try to address this problem of only having the reward at the end, so whether the task was successful or not. And it works, and why it works, because we have primitive skills. So we have pre-trained primitive skills. So array actually is interfering. So the search tree is not huge. It's limited. Okay, may I just show the some demos. So here's the current setup. So it's trained in simulator with on ShapeNet. So we can train it on all kinds of objects, different types of cups. And so it's quite robust to, well, it is robust to perturbations, because so the planning is inside the network. So if until it grasps the cup, so it will not stop. Oops. Okay, so here's another example of robustness. So we just fool it and occlude the object. So it goes for the next object. And actually, this video stops, but it does go for this object and completes. Okay, and that was very short on robotics, and this is the summary. Okay, and if I have 2 minutes, I want to, yeah, okay. So I have the Second Life, which is the company as many of us have nowadays. And this company is, well, it's been small now. It's already about 100 people. And it's been originally in Moscow, and actually now we are, since 1 year, we are also in Amsterdam. And okay, hopefully that's what big bosses think, that it will take over the world. So what we are doing, it's currently it's mostly focused on faces, and we are happy to do it quite well so far. So this is a NIST evaluation. This is the largest evaluation for face recognition, and so we are not only good in accuracy but also in performance. So this is a computational time versus accuracy performance. So we are quite far from competitors. And also, okay, we are looking at other things like anti-spoofing, also related to faces or like emotions and so far. But eventually we'll be expanding to other areas, hopefully. And so, because I'm here now in Amsterdam, I had to bring this slide. So yeah, we are looking for. I know many companies are looking for computer vision researchers, but if you're interested, we'll be happy to talk.
Great.
Okay.
So there is time for a few questions only. Any questions?
A two-part question. When it comes to, I saw that you have 1.3 million videos that equate to 130 million clips. I assume when you're teaching a robot, a robot to do a task from a video, that the training data has to be very, very high quality, and lots of experiments and testing in that quality. I was wondering, my question is, what do you use when you're doing these things at scale to structure that data and turn it into higher quality? So text labeling and labeling and turning that video into high quality training data.
Right. So your question is, because we did not really connect instructional videos to robots yet. So your question is more like how to manage it in the future.
How would you manage it?
Yeah. So how to get the clean data to. So do we really need like clean data for robots? So that's a question. I don't know. Maybe it doesn't have to be super 100% clean. That's the hope, because otherwise, yeah, I think it's maybe relates to another question which is very important: how you train from few samples, right? Because kids they don't need millions of trials to grasp a cup, and maybe if we can train it from fewer samples, then we would have more cleaner data. It would be easier to clean the data. So maybe these two questions are related, but we don't know answer to neither of them yet. So like training from few examples, it's it's complicated.
I have a question. So maybe I missed it, but when you get instructional videos, the point of view is like third person, whereas if you're having robotics, it's obviously first person. So
Okay.
do you have a way to actually handle that?
Right.
Because the visuals will also
Right.
change.
Right. Okay. In robotics, what we now have, it's also third person, but that's okay. That's where you put the camera. But you are right. For example, if you want to give instructions to people, like if you have this wearable glass, then it is third person. So indeed, that's a very good point. So I know I've been to a few papers, Cordelia also, for like domain adaptation, when you try to learn actions from one viewpoint and then adapt for this third viewpoint. That's one. Let's see. Yeah, I think it's a good question. I don't have a good answer. I think, well, if you really want to like do practical application, I think putting a camera on the side and having the third, actually the more cameras it is, the better in general it will be. Even like having multiple third view camera.
Probably robots will have like mini cameras.
Yeah, exactly, yes.
As well,
yes. And we see that like if we do put multiple cameras for the robots, so if we put multiple cameras even without calibrating and doing anything, just fusing the signal, it works better. So
yeah, I'm just
yeah.
Other questions?
You obviously have annotated data. When you showed most of the videos, it was mostly you were classifying the actions based on whether the fridge was open and the fridge was closed. But I would feel like the person doing the action and the action dictates would contribute to deciding what action is happening on the video. So I don't know, like, do you not believe that some kind of post-estimation or something like that would help in action, this kind of classification?
So you talk about this second paper, which were the state changes between objects, or?
Yeah.
Okay, and then having explicit model of a person in there. That's, yeah. Yes. I mean, that's the question how you model action. So we do model action. That's the, sorry if I didn't understand the question, but we do model the action, and we assume that the action is related to the object, right? So there is a temporal relation. Maybe your question is more about spatial relation, that if there is a fridge, there is a person, there is a spatial interaction between them. Yes, indeed, there is, of course, lots of knowledge to gain from this, but we didn't look at this.
I would feel like if you show CNN most of these videos, they would just learn what action it is based on the colors or the texture of the frames.
All right.
What the person is doing.
Because like if there's a fridge, it will just learn that it's opening a fridge. Okay, so we are actually doing localization, so it means that it has to find the right moment. So it sees the fridge all the time, but it does have to find the right moment when it happens. So I imagine, I agree that most of the action classification methods, they actually probably look at just the objects, not the actions, but I think if you have to localize, I think there is something more happening.
I think we have to enter the room now because our slot is over, but let's thank
Okay.
Ivan again.
Okay, thanks.